Hello, today I would like to give the second lecture on Calculus 2, and our aim is defining the known number sets. Last time we have defined video numbers, and that has taken up the whole lecture, and this time we would just like to define all the other known number sets. That would be first of all the natural numbers, and based on them also the integers and irrationals. Okay, to define the natural numbers will be a little bit of a challenge. It turned out that we'll need an additional axiom complementing the already stated axioms about video numbers. And I should remark immediately that the axiom that we will introduce is not a customary one. It is my own invention because I saw a gap that must be closed for the proper introduction of natural numbers. Okay, let's first title it properly. Calc 1, lecture 2. This will be a little bit of spontaneous lecture because I would like to try out something new. Namely, well, how should I put it? Spontaneous but proper thinking. Because usually when I'm thinking spontaneously, um, I'm not quite trying seriously to follow what I'm thinking because I know that it will be approximately true, but this time I would like to really follow it. Right, but nonetheless, it will be a legitimate lecture, or at least I think so. That we will see. Okay, let's call it an addendum to the defining axioms. Those will the three things that we stated to be defining axioms of real numbers. Again, I recommend you to increase the pace by multiplying it by 2 using key functions of the YouTube videos because it is probably advisable. I'll also try to write accurately so that it would be quite warranted, I guess. Okay, first of all, let's give a customary definition of natural numbers. We'll need this special axiom to define the natural numbers in the shape we know them. But the thing is that first, our definition of the natural numbers will be very abstract, and for this abstract definition, we do not actually need this additional axiom. We need this additional axiom to get from this abstract definition to the common representation of the natural numbers as, so to speak, sums of 1. Right. Okay. Well, so let's say that this is we'll proceed here later. But first give the nature definition. Well, this in our setting it is nature. Definition is quite abstract, but nonetheless. Okay, first let's call this section defining the nature numbers. Okay, the first definition that we need is a definition that introduces a special type of subset of real numbers. We define so-called inductive subsets of reals. And why they are called inductive, you will see in a second. A subset M subset of R, of our R defined in the first lecture, right? Satisfying those three chapters of properties, right? A subset M of R is called inductive if it satisfies the two following conditions. If both is satisfied, 1, 0 is element of M, 2, well, for each x element of M, we just have that x plus 1 is also element of M. So this is just such weird sets that if we knew what nature numbers were, if we knew already about the nature shape, that would just contain the nature numbers, right? But not only that, those are certainly sets containing the nature numbers as we know them, but of course we can't use our knowledge of nature numbers because we have only properly introduced videos, right? And let's state this the third one. I don't know yet if we would need that, but I think so. That this said, okay, non-emptiness is already given by 0 element M. So, despite me saying that I will think properly while writing, there is just some lapse between realizing what you have written and you have not written, because the focus shifts, the focus of consciousness shifts, and so it is like that. Okay. Oh, this is an inductive set. Then we define the nature numbers. It is a kind of a theorem because we have to claim something, and we claim theorem intersection of all, let's call it again M, subset of R M inductive. So this denotes just intersection of all inductive sets in R. You can get used to this notation. This is just intersection over all sets that are contained in here. We could write it in index notation with some trick, but it would be just a trick, so I write it like here, right? But don't confuse it with anything else. This is just intersection of all sets contained in the set that is specified here. All right. And this set notation, like I'm explicitly describing the elements without specifying like elements of something with certain property. This is perfectly fine because this is just defines some defined set, and then this is fine. All right. Is non-empty, which is actually obvious. Is inductive. And that's it. Of course, it is a subset of R. We could also state it here, but since it is all subsets of R, of course, intersection of all things would be subset of R. And then let's call it theorem and a definition. Then we call n defined as that intersection. This set of natural numbers. Okay, so that thing is called the set of natural numbers. We have now introduced him very abstractly, but after introducing this special axiom we are awaiting, we will just show that it is the natural numbers as we know them. All right. Okay, there will be a little bit of preliminaries for that, but in the end we will just establish that. Okay. Well, the proof of this theorem is very simple. Proof, just recall what the intersection is. Well, we can already use this notation at least. Since 0 and m subset of R for each inductive m. So recall that the property of being inductive by definition included that 0 is in the set. Inductive m subset of R. Alright. Alright, and recall this definition of such an intersection that just meant that the elements in such intersection are such elements for which it is true that they are in each of the intersected sets. All right, now we already have that 0 is in it, and now show, because well, we have used now that 0 is in it to show that it is non-empty, but of course 0 is in it just is an intermediary step of our reasoning, right? Now show for x and that x plus 1 element n, but x element n implies x element m for any inductive M subset of R, right? This is just the definition of N as intersection of all inductive subsets of R. That implies for this X, that implies X plus 1 and M, because M is now inductive set, right? X plus 1 element M for each inductive M subset of R, right? And thus X plus 1 element N, because X plus 1 is now element of each inductive M, and so it is element of N. And that finishes with proof of inductivity of this intersection, which we call N, because we have just established both the properties that inductivity requires. Okay. Now we'd like to have the following theorem. For a statement P applicable to, let me think a little bit. It doesn't matter, so let's say that this statement is applicable to natural numbers. That is, it is applicable to all of the natural numbers. And let's say it is applicable to natural numbers from number. Okay, we don't have anything like that, so yeah, applicable to all natural numbers. The statement P applicable to natural numbers. Have that if this set of X and R with P of X true, so the statement is true. We set of such so that this set is a subset of the natural numbers, right? That is, this is already taken out of the natural numbers, where natural numbers are understood in sense of our abstract definition. Okay. You could also say to real numbers, and maybe it's better. But on the other hand, to real numbers, that would be a little bit restrictive. You're only interested in nature, so let's say that we only take a statement applicable to natural numbers, and we just have x and then p of x is true is equal to n. So we define the set so that it is already subset of n, right? So we just define the set of all x and n so that this statement is true. It is not necessarily the set of all elements in n, but we now claim that this is also true, because that direction, that subset relation is automatically true, because by set condition we just took in this set elements only out of n. So obviously it will be a subset of it. Okay. Okay, and you probably recognize, maybe not yet, but you will, that this is what we stated as an axiom, namely induction axiom, in our uh, videos and basics of university maths. Okay, but now we can prove it because we had that abstract definition of real numbers, and from the nature numbers, nature result with this property. Okay. Okay, how do we prove that? Well, let n 10. No. We don't need to do that. We just need to show that it is an inductive set, right? Um, okay. Something is certainly not right. Uh, that's interesting. I'm noticing that working in information different streams simultaneously doesn't work quite well. Okay. Of course, we need for that to even make sense, and then it is arithmetical. By induction axiom, of course, we didn't just have that we take all numbers in natures for which some statement is true, but we also had it is such elements x in n, such that p of x is true, and such that for all have that, let's phrase it maybe like that, and there is of course if condition, if p of x implies p of x plus 1. And the proof is very simple, and in that case we don't even need to state theorem. Proof under the stated condition, but we need it like that because, well, because remember our induction axiom in the basics of university maths, and there we had to have this condition, and then okay, I should also say that of course we take 0 to it because, well, we need to have inductivity, right? So if there is this 0 is inside, then it is just the set itself, right? So then we automatically have the induction, we start induction anchor, or we already have in that set, right? We have 0 in it. But if 0 wasn't there, when we have, of course, to add 0, right? And well, we also need to have, okay, yeah, I didn't think of that. Okay, so I'm noticing that even by proper thinking, if I didn't think of things in advance, just coming up with things happens in steps, because of interrelationships by formulations of theorems, I have to recall the structures again, and then I have to recall the structural connections, how exactly it works. Right, and also have to do a little trial and error in mind. Okay, so unprepared lectures have to be a little bit messy. Okay, wow. I'm really wondering if I could do better at that. Okay, let's just proceed. But generally, I'm just wondering. The statement P applicable to natural numbers. With, let's call it corollary because it doesn't deserve the name of a theorem anymore. And this is just the induction property, right? For statement P applicable to natural numbers with P of 0 is true, and P of x and 4 and R x P of x is true, implies P of x plus 1 is true. Okay, well, have to think here a little bit because P applicable to natural numbers, and here we talk about videos. Well, okay, here are different problems depending on how I choose to formulate that. If I choose to formulate this as a statement applicable to real numbers, so of course it has to be a statement about numbers generally, and the largest of the most capacity thing that we can have is applicable to real numbers, right? Then I can have that. But for a statement that is only applicable to natural numbers, would still like to have this theorem or this corollary. Okay, and so I would like to just say that because we're only interested in that, let's say it like that. And P of x is true implies P of x plus 1 is true. Then adjust by our definition of the inductive sets. We have that the following set is inductive. If then what do we have? Then the set of x and P of x is true. It's already equal to n. Okay, just like we had, this subset relationship is obvious, right? It is stated that all elements of that are already taken as elements of n, certain property, right? So this subset relationship is obvious. And the opposite one, well, we recall that n is intersection of all inductive sets, and we have just then, or we could get this subset relationship since it is an intersection, just showing that it is an inductive set. But since P of 0 is true, 0 is in this set, right? And since we also have exactly that condition that for this set phrases the inductive condition, so for x plus 1 is in this set, we have indeed that it is an inductive set, and so Indeed, n is subset of that. So, and you can also see immediately that it is the induction axiom that we had paraphrased, because we just have a statement equal to natural numbers, and we have p of 0 true, and we have that we true for p of x for x in natures implies we true for x plus 1, and then we have that this statement is actually true for all natural numbers, because this is exactly what this subset relationship tells us. Okay, well, now we would like to have, okay, now we would like to have a look at this axiom. But first, let's state what we are trying to do, because that is, as I said, for what we will need this axiom. Now our goal is to establish the familiar shape of natural numbers as n is equal to 0, 1, 1 plus 1, 1 plus 1 plus 1. But well, the problem that we are facing here is that this dot 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 is not actually explained in any way. There's no mathematical procedure with which we could just state it, because we don't know what this is supposed to be. When we just write it down for a certain expression like that, this is not defined, right? And this is defined. This is defined. We can apply our operation with a certain number of times, and pay attention that my using number of times is actually not correct, because we don't have natures yet, but I'm just abusing the nice properties of a language. That language can be used without mathematics. So yeah, applying that a certain number of times will give us some number. Pretty fine. We can also see that it is a natural number, because we see 1 is a natural number, because 0 plus 1 is 1, and 1 plus 1 is again a natural number, so we can conclude that this is indeed a natural number. Alright, but what this is, we really don't know. We don't have it, because we don't have any arbitrary addition. So there is a need to somehow introduce it mathematically, but clearly from what we already have, it just qualitatively differs. So it is not a thing which we can derive from what we already have. And that you can see in that you think that we actually think now about all possibilities to add a number of ones. We have not stated that it is possible in any way, right? And we can think of a general addition of a number of ones. And exactly that we would like to make solid now. And we call the objects that we are introducing, or the idea that we are introducing, the iterational axiom. What exactly does it do? Well, it does the following. We will state just one version of it. There might be different versions, but we'll state just one because now we just like to use natural numbers in subsequent for counting, which we already assumed we can do in the basics of university maths, where we introduced that sigma notation, where we use the natural numbers of counting for counting already. But yeah, we actually can't do that yet because we haven't introduced the natural numbers there from your shape, so there's no counting for us, if we are honest. Okay, iterational axiom, and that just states for a real number a element R the procedure, and this is just a new object that we just define as follows. We could try to formalize it more, probably, but there's not necessarily need. Procedure a plus a plus a plus a plus a plus a plus a. Oh, what do we do now? Now it becomes a little bit tricky. We could state at this point a procedure that is defined for any number of times of adding a, but we don't have this number of times, so we'd like to circumvent it, and the question is how we can circumvent it. Okay. And let's put those dots, but let's put them and explain. The procedure is defined given subset T of R such that the procedure thesis defined as V is an infinite recursive process. So, defined as a recursive process okay, take T 0 and T shouldn't even use something like that. Take T element T define as a recursive process. Let's say using a map. No. Okay. Define this using a map. What kind of map? Well, take C T and using a map, let's call it F. Take T element T and F maps T to A. Keep that in mind. And take K element T without this T. Then F maps that K to A plus A. Then of course take L element T without T and K, and then F maps with L to A plus A plus A. And so it goes, and you see we are kind of circumventing the issue that we cannot add immediately a plus dot 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 plus a, in that we are including all the intermediary steps, but are making dot 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 in sense of allowing for uh, repetition of the steps of iteration. And yes, we are kind of conceptually, nonetheless, introducing natural numbers. uh, so, I mean, without properly mathematically defining it, but it happens on a linguistical level where we just know that if the procedure is described that way, then we can repeat it again and again. Right, so we are kind of transferring the issue, but well, it is just that some things are mm, only allowing you to get peace of mind, so you can formalize them more and more, and you can always find a more vigorous formalization. But yeah, you are just shifting that, and that's where I decided to stop. Okay, so in the procedure thesis, we understand what it means. So the axiomatic thing here, the truly axiomatic thing, like structural axiomatic, is here this thesis. The axiom is we understand what it means, the procedure thesis. Right? And in case of such a procedure, it is valid because we totally know what it means that it ceases and what it means that it does not, right? Okay, if such a procedure ceases, call the output so call the output of the procedure, call it just a t. So this is a with the sub-index of the set with respect to which the procedure ceases. And you see, yes, we are just transferring the issue somewhere else. We assume that we understand the word cease, what it means when procedure ceases and what it means when it doesn't. Of course, it is not a perfectly mathematical definition, but if you look up the very basic axioms of mathematics, they still work with words. You can't you can't um, remove all the connections to what are the means, the vehicles of our thinking. You just can't. That's impossible. Okay, where the output is the value of f defined by the procedure in the step after which, and that means that the procedure ceases, right? After which t is empty set. That means that the procedure ceases. That just means that t becomes eventually an empty set. because after that we can't take elements anymore, right? And yeah, it is, if you think why it is actually seems to be fine, we know sets for which the procedure ceases. Such a set would be, for example, a set 0 or set 0, 1, right? There's no problem with that. For those sets, the procedure certainly ceases. So it makes sense to talk about this procedure ceasing. If it is ceasing for R, well, we just don't know. Okay, we don't know. Maybe, maybe not. We don't know if it ceases for R. We simply don't know because we don't actually have anything. We have not encountered anything in R that is not 0 and 1. We don't know anything else yet concretely, so yeah. But well, we can just think that we could come up with numbers like 1 plus 1, 1 plus 1 plus 1, and we could do things like, of course, because in R we can also like take the inverses. Of course, I mean that this would be just the inverse of that, right? So we could apply one operation, then apply, we would have an inverse for that. We could look at multiplicative inverse of that. There's no problem with that. But we could not actually know if R has that R, and for R the procedure would never cease. Maybe it would. Maybe R is not as large as we suppose. So if our definitions give that it is large or not, we actually don't know yet. Okay, well, having iterational axiom, let's establish a familiar shape of L. Okay, well, so theorem each output of season. Let's do it like that. Stated in mathematical English. The following sets are equal. X element R such that X there is T subset R such that X equal 1T. Recall what was 1T? That was iteration by T on the number 1. Right. Is equal to n. Well, let's try to prove it. I don't know if it works. I think it should work actually, but I'm not sure yet. Okay, because it might be that this theorem actually is not provable in that regard. Maybe it's difficult to prove too many steps at that point. I don't know yet, but let's try to prove. Let x t oh, certainly an element of R, because here all steps leave it as element of R. Okay, let x element 1t. Okay, then since iteration ceases, then yeah, of course, we should think about what we are actually allowed to do. So such iteration ceases. Okay. Then what does that mean? We defined iteration like that, right? Then we could write 1 and 1 plus wait, of course it is not all, because we also need 0 here, right? Okay. Okay, yeah, that's right. We need 0. Good, right? And what I now mean that here, as in a sequence of such repeated steps, I don't mean a number of ones. I don't count the ones. I just repeat the step of adding 1 to the previous result. I can do that, right? And then at some point, in that way, I end up at x. I end up at x. Okay, by definition of iteration. By definition of iteration. By t on 1. By t on 1. Okay, then x is obviously element of n, because 1 element of n, because 0 element of n, and 0 plus 1 element of n, because n is inductive, as we have shown, because 1 element of n, and x resulting in a sequence of steps preserving being in n, preserving being in n by inductivity of n. Okay, well, this works, why not? So indeed, x resulting from 1 by an iteration of addition, and each subsequent step certainly preserves being in n, right? because we can't say that about that without knowing it about that, but we can say that, right? And in case you are wondering, just use induction without iteration or axiom would not work because we could not even write this x down. That was the problem, right? That seems to be applicable, like we just established previous step is in n and everything is fine, but the problem is we would then only get the problem is we could not apply that statement to elements in n if we would try to start at this form. But if we would start at elements in n, then we could not apply to an n a general statement of being a sum of ones, because being a sum of ones can be only defined iteratively before we know what is a number of additions of 1, right? And that is why we needed the iterational axiom necessarily, right? As I told you, this is not a customary axiom. This is usually missed in lectures, also because that is kind of not that nice mathematically, but yeah, there's actually no avoiding it. You can't avoid it. Okay, then now let an element n. And what we have to show is that is actually that there is a procedure that certainly ceases. Right. How do we do that? A procedure that ceases. Okay. Well, show then that the procedure one n. Okay, how did we do that? Yes. Then ceases and gives n. So what we'd like to show is that if we iterate over this set, then indeed what results from it is a ceasing procedure, right? All right, and that for any n in n. Alright, we have to show that your procedure sees gives not this n, of course, but our n. Yeah, this is mistakes that just happen. And gives n. Alright, how do we show that? Having only our very special shape of the natural numbers. Okay, well, this is actually a claim that is perfectly well defined. So define the claim P for natural number n element n. Here is the procedure 1 sees and gives n and gives n. It has, we know what it means that it gives n. Sees and gives n, or n equals 0. Right, then claim and then P of n is true. It's inductive. Okay, let's see if it actually works. Well, P is true for 0. Obviously, it is defined like that. Right, I mean, the claim is true for 0, right? Now, let the claim be true, because that is the condition that we have to establish to well, yes, that is a condition that we have to establish in order for this to be in natural numbers, right? P is true for 0. Now let the claim be true for n element n. Then 1 seizes and gives n. Alright, or n 0. If n 0, then 1 1, then 1 1, and so obviously 1, can write down the procedure. That is 1. Yes, 0 plus 1 is 1, and that is, yeah, then 1 is plus 1, and if, don't forget, we don't have it, and if we would have established how, you'll see in a minute what we don't have, would have established one is equal actually we should take smaller than n, because otherwise we would get you always one bigger, because we would have here here for example 0 1, right? So and if you would have okay. Oh. So one guess, of course, because we kind of start at 0, right? Nature 0 is nature numbers, so yeah. Okay. Okay, well, we should have established that that is indeed, wow, what am I doing? I mean, we need that set, but we need that set without 0. So, that's better. Right, we need that set without 0. And it works. Okay. Let's look at it. And we have to establish that, right? We don't have it yet. But we'll look at it and we will establish it. We would have one equal indeed 1 0 1, and that is already done. So to establish that this is actually 1, we would have to establish that this is the set containing only 1, because this is not clear yet, right? We don't know it. We don't know if n0 nor equal 1 does not contain a lot of things. We don't know if it contains only 1, but we should establish it. So, and then we would have established that for the case n equals 0. You see, that is one of the cases, right? If we are done with that case, then we can proceed with that case. Right. And we can see that it is an exclusive case, because 1 plus 1 plus something 1 plus 1 many times will be always bigger than 0, just by properties of bigger with equality, if bigger with addition. So yeah, it is an either or actually, but of course we formulate it in terms of or, because that is how we learned the logic of statements, right? So let's call it a theorem. And let's phrase it, for example, like this theorem. For any natural number, let's call it auxiliary theorem because we needed to prove that higher theorem. Let's call it auxiliary theorem. Also called lemma, but okay, I called it auxiliary theorem. Any natural number n have that is set of all x and r, the property that x is between n plus 1 is actually equal n plus 1. So all the x that are in between already accounted for in here. Right. And then that means in particular, since every natural number, do we actually know that any natural number should be bigger or equal 0 if that there are no negative natural numbers? Do we know that? Well, we actually do not. We do not if there are no, we do not know if there are no negative natural numbers, but well, if 0 is in every inductive set, then 0 plus 1 is as well. Okay. Yeah, we really don't know if there are no negative natural numbers, because actually our definition of inductive sets could very well, as I see it could very well include all the integers. Okay, so first we would actually have to prove that we do not have negative natural numbers. Okay, well, I don't see why that should be true. Actually, if I'm honest, I don't see that. Well, let's assume the positivity for natural numbers. Okay, yeah, that indeed follows. Finally, because positivity is inductive property. Okay, well, let's call it maybe remark. Since positivity is inductive property, we remember positivity as being bigger than 0, right? Inductive property defined in terms of that comparison relation bigger or equal. Call the exact definitions. Since positivity is inductive property, have that natural numbers are not negative. In the inductive property, I mean if a natural number is positive, if a natural number is positive, exactly, then the natural number plus 1 is positive, and this is also even true for real numbers, which just means that we set with the defined by the claim the number is positive, the subset of natural numbers is inductive, non-negativity. Let's call it non-negativity to include 0. Since that set is inductive, we have that it is just equal to the natural numbers, since non-negativity is an inductive property. Yeah, that's actually interesting. Okay, negativity isn't. Okay, wow, huh. Interesting. So it is because we take the plus 1 that that the natural numbers are actually all not negative. Numbers are all not negative. So if you couldn't follow that line of reasoning, just write down this set with this claim. Are non-negative. Okay, so they are all bigger than 0. And we know that this thing, this bigger or equal, gives us an ordering relation, as we said, just because the relation is true for any two real numbers. So it is transitive, so of course it gives us an ordering relation. Basically, which exactly an ordering relation means that we can order numbers like that. Then we can just start at 0 and we can go in this direction, and there will be the natures, right? Alright, and all positive numbers are here. We could depict it like them, like that. But okay, the interesting thing is they are non-negative, which means that is actually numbers between 0 and 1. Okay. So if we actually exclude 0, like done here, then of course the thing that we will have here will be just x from 0, and 0 is prohibited, so here is strictly bigger, to 1, because 0 plus 1. So that would be exactly 0, 0 is excluded, so it would be exactly only 1. So that would be exactly what we want here, right? Okay. So that would in particular imply what we need there. Okay, proof. Oh. How would we do that? The thing that one thinks first of probably is to show that there is no natural number in between 0 and 1, exactly that. And from that we could then conclude that, right? But how do we show that there's no natural number between 0 and 1? What's the problem there? Well, perhaps we would need additional knowledge for that. I mean, could be established immediately here, but perhaps it is not a good idea. Let's see. Well, how do we show that there's no natural number between 0 and 1. Well, suppose there is 1, then it is in every inductive set. Right, so it is in every set. That contains 0, and that contains 0, it contains every successor of a number. And by successor, I mean just adding 1 to the number under consideration. Why would that be a problem? I don't see a problem with that. So having natural number between 0 and 1 seems perfectly feasible. Why not? Well, certainly we would like to use the property of natural numbers, that is, intersection of all inductive sets. That is, there should be, or at least we think that, there should be an inductive set that does not contain any numbers between 0 and 1. And let's do this set very simply. Let's just take this set, proof, define an inductive set. And that it is indeed inductive, you could prove, but I will explain it shortly. And define this set as 0, it has to contain 0, also it contains 1, and that is just x bigger than 1. Okay, why is it inductive? Well, because if we take 0, then clearly 1 is in the set just by definition that 1 is in the set. Okay, if we take 1 and we add 1, then clearly the result is positive. Well, maybe I have to illustrate that for you. Let's call it auxiliary theorem. A bigger than B, C bigger than D, implies A plus C bigger than B plus D. Probably can see that immediately, but okay, let me show that properly. Prove. Well, we just have to conduct. Oh, I forgot. We have to cook up suitable comparisons and then use transitivity. So what would be suitable comparison? Well, A, B implies, well, what do we have here? A plus C. So we have to come up with A plus C. Right, B plus C. And of course, B plus C we have here, B plus D we have here. So what is missing here? B plus D to make the transitivity link. And C bigger than D implies B plus C bigger than oh, what? Yes, B plus C bigger than D plus B. Okay. By transitivity, we have now both statements, right? And by transitivity, because I'm looking at this one and this one, and that is exactly transitivity. Read like this, right? Have A plus C, D plus B as wished. And of course, it also works with bigger or equal, small or equal, and whatever, just to use those negations, or somewhere also ors and things like that. Of course, I won't prove that all, but well, the spirit is clear, and you could prove that all if you wish. Define inductive set. This set does not contain any number x element r with x bigger equal 0 or equal 1, because it does not contain any number of smaller any number that is smaller than 1 and is not 0, so it does not contain any such number, and hence, since in the intersection, which is n, we in particular intersect this set includes all possibilities for such numbers in n, and hence, and thus neither. Okay, it's clear. Okay, okay, that's not clear. Sorry. Hence, and thus neither. But we are interested in the more general statement. Of course, we only need that statement for our theorem, but it's a nice statement. Why not have it? It's also kind of in the spirit of what we are trying to prove. So let's prove that maybe immediately. But actually, it will be a result that will completely result from that, from what we have here. Well, yes, because we will have established that the sums of 1. Ah, okay, so we don't need that. We actually do not need that. Okay, let's do it like that. This part we need for our perfume. But the general part seems to result from it. Seems to result from it in turn. Result from it in turn. If it is really like that, well, we'll see in a second. Because so I can't do that all the steps in mind immediately, or probably I could, but it would take time. So let's do it. So the theorem below establishes what does that establish? Well, exactly one equal 1. Okay, that's perfect. And now let 1 and 0 small or equal n be equal n, right? Because without because that's additions of 1 couldn't be 0, so yeah, that's our case. Now let well, and with that we have established what? Well, p is true for 0, claim is inductive. Now let me claim p true for n element n. And now we have proved, well, now we have proved the part of inductivity property that the successor of 0 is in the set. Okay, now let's 0 n and show that is weird. Yes, here we need that. We need that is more equal n, because here we have plugged in 1. Here we have general case where that is smaller or equal n, and show 1 n equal n plus 1 is equal n plus 1. But that is pretty simple. Obtain from, well, what does it mean that this actually is non that it is a ceasing operation obtaining that? Well, that means just that, yeah, right. And we just know that it is steps that are ending 1 and whatever, and that would be then we mean that last step, right? That would be n. We don't know the number, right? But we just know some number of steps, right? We don't know some number of steps, but we know we can write down the steps and end results from it, right? Obtain from that the extension of this operation by step, we just add one step, right? Plus 1, right? Yields exactly so we just add this another step, and this certainly results in n plus 1 because we have just added 1 on both sides. Yields exactly oh, what does that yield? Okay, so we need that because again we are facing this problem. We don't know what is actually smaller or equal n because we only know that this operation yields that, but we don't know how for any natural number n, and that's not here, p of n is true is inductive. Well, actually, we only need to show that this is an inductive set, and then it already contains all natural numbers. right? And for that, we don't even need to. Okay, oh, we need, because there's a reference to natural numbers, right? Same game as here. If we now only have that that we can extend it by one step, then it yields, of course, that the extension of this by this one step yields us n+1. But we don't know if this set here contains exactly all the natural numbers, contains exactly the numbers 0 to n, because there might be numbers between n and n+1, right? Okay, well, of course it contains numbers 0 to n, but yeah, we actually need that. Okay, then we should also add it to our induction. Maybe do it in another way, because that certainly contains 0 to n, right? And we know that between 0 and 1 we don't have anything, so that certainly is clear for 0 and 1, but it is not clear for other stuff, right? So if we now have this n+1, then we should actually have had already that for n, we don't have any numbers between 0 and n. Okay, well, okay. I think we should prove that. Then we should prove that we don't have any numbers between 0 and n. Maybe we'll add that to the theorem. I don't know. If we have that we don't have any numbers between 0 and n, then we can do that step properly. Okay, well, we actually need that. Okay, I understand. Oh, okay. So the theorem doesn't work, just like I thought, but I wasn't sure. So, but we only need that to proceed here and to show that we don't have any numbers 0 and n for any n, right? And this easily results from that, right? It will be just a corollary. Okay. No, it is actually coupled with this result. So yeah, it will be a little bit of work. Okay. Well, how do we do that? Well, let's now n element n. What we will do? Well, we will do simply induction. We'll do induction again. All right. Well, let now n 10. And show the statement is true. Let now the statement, let now, okay, I should think more about what I'm writing. I know I promised to think about it, but like, constantly forget that I promised to think about it. Let now the statement be true. And you know what it means. We are trying to establish the induction condition. I'm not stating it explicitly anymore, but we are trying to establish it for this set, right? For 0, it is true, right? Now, let's the statement be true for n element n. And we just like then to to establish that then the implication of a statement for n plus 1 works. Right. And show. And we have the n core at 0. Then show n plus 1 x, and we know that it is x in your numbers is exactly 1 and plus 2. Oh, suppose there is x star section n plus 1 x n plus 2. Then, pretty clearly, in x minus 1 n plus 2 is 1 n plus 1 minus 1. Contradiction to here is no x element n plus 1 n. Now in contradiction to what we had to x between n and n plus 1. Okay, and then that proves that there's none, and this claim is proved. Right, now we'd like to have a corollary. Okay, that is coupled to that actually. Okay, that is coupled, no corollary. We have to state it here, and we have to state it here as additional part of our induction. Okay, well, in claim, and we define the claim P. For a natural number n, the procedure ceases and gives n, and here we'd like to continue to write, or n equals 0 comes in a different point. And gives n, and we have what do we have? 0. And without 0 is without 0, right? 0 x, and we mean of course x in R. What else could it be? X n is equal 0, is equal, in that case 0, 1, 1 plus 1, no, let's do it differently. Let's do it differently. It contains all the elements. We don't want to do that actually. We want to circumvent it. uh, we just add that is -1, and we just add n. We'd like to have that this though this edit is exactly n. Okay, well, we procedure ceases and gives n, and we have that um, zero, or n is equal 0. Okay, n is equal 0 again is true, then we have to show that it is inductive, then we have that for 1, right? And we have that 0 to 1 is indeed 0, which is united with 1. So this is true, right? Because that we have just from that. Okay. Okay, so if we construct we claim like that, and it is of course true, no problem. Then we have that more general case here below. Now let n show and um, that is x, of course. X a negative number, x and plus 1. And we also have something conditional that is actually n. And we also have something conditional. We have that is now, and now let that, and let also what we have here n, and that is equal to plus 0 x plus 1. Okay, that is x. Okay, I've written it badly, of course, but you understand what I mean. I mean such x and I are such that this is equal to this, right? And this is equal to 0 x and -1 n, which is important here. We obtained from that that the extension of this operation yields exactly what? Well, we have to look at that, and we have to look at that. Now what do we have? We have that there is indeed only those numbers that we have there, right? We obtain from that, and we obtain from that, and we wanted only to have that um, excluded, right? We wanted to have that excluded, and we wanted to have that there are no additional numbers coming in, right? And indeed, as we can see here, actually not here, I should of course refer to this here, right? Because if we like consider that here, and we consider that here, then we see that when we consider this, when we consider this, then that is of course just sit with nx and plus 1. You can check that via using the definition of those bigger or equal and so on, from which it results that plus 1 is just same as so we actually didn't or did we need to have that by induction? No, I think we didn't need it. Okay, we didn't need it. Okay, so we didn't need it. We just use here that statement because we only need to add as an element the n plus 1, and that just works with that smoothly because that means that that is subset, right? Just by how the sets work, that is subset of that. And you can check that it must be true. Because, well, this is not in that, so it has to be in that. And the other way around, this is not in that, or only n is in that. And so that has to be in that. And maybe I should do that. That's better. All right, yeah, that's better. And we have that. And then, of course, equality, because that is also here. Right. And well, what does it mean? That is exactly what we needed. Yields exactly 1, 0, n plus 1, or n plus 1. Since, oh, we just know what this now contains, right? And we just know that what we have taken here, well, what we know was that, right? So that this actually contained we know because we went through this set. That is how iteration was defined. That is, this pictures exactly the set, right? So that would be, if we went through this iteration, then that would be exactly the additional step. And what we needed, that this is exactly that set, right? Because it could be that we do this additional step, but this actually not matches this small or equal, because there could come in additional numbers that are not in this set, right? Iteration would be defined, iteration, another step in iteration, yes, but that matches exactly the set. And we write the steps that exactly we maps to that, maps to that, maps to that. For that, we needed that only one additional element is added here. And by only one, I don't mean that we kind of use numbers for counting. No, we don't do that. We just see, well, the element that is added, which we have to map, is exactly the element that remains here, and after that the set is empty. All right, which yields exactly, well, how do we write that? Which yields exactly, well, let's write since maybe first. Since and 0 and plus 1 is exactly 0 x n, and that is important part. Oh, since we are moving 0, we remove 0 here, right? That we have just proved that it is the case, that here, right? And that is actually n0n, right? And so joining n0n, which was the iteration here, just by assumption that that yields this. So this set is this, right? So we could just write this yields that, since that is that, which is then, well, we just look up what we have here and I write this set in a funny way, but it is just, well, that iteration that you know, right? Okay, and we said that this is exactly that iteration, right? Which went through each number in here. I have wrote it like this, right? Which went through each number in here, so it is certainly that. All right, this is thing, and this is n plus 1, because this is how that union of sets works, right? So this is exactly that set, and now we see what? We see we have joined exactly this, and when we do this by this operation, this matches exactly additional step in this operation, which proves that this is indeed n plus 1. So the trouble was to establish what is actually this, right? And now we established, yes, exactly. We join this element, and this corresponds exactly by extension the operation by this step. After that, the set is empty, right? So we call the definition of operation, and when it ceases, after that, the step is empty, so the result is exactly that. With that, it is established. That establishes inductivity of set. What did we call it? Something satisfying P of n, right? Well, n element n, P of n is true. Yes, that establishes inductivity of set P n element n such that P of n is true. Hence have n element n, P of n is true. Is equal to the nature numbers. And with that, n is equal to 0, 1, and 1, 1, and if we have established that, then we know that it is like the next thing, and we know from the adjoining what this next thing is. We know that this next thing is exactly that operation step, another step, and with that we know that this next thing, if we also think of that theorem that told us what numbers are in there, right? And we know that if we order those numbers increasingly, also compare those intervals, then we get that result of that operation. Right. And now we are allowed to write this, because by that we just mean the results of the respective operations, right? Right. Of course, it is like just making some tricks. That's obvious, because like writing the result of those operations, what is the difference from um, just writing that down like that? But there is a difference from just writing it down like that, because the operations are now defined objects. If they are defined objects, then that just means that I consider all the operations, right? I consider all the operations that are defined in that fashion. But the wonderful thing is that I now am using the set itself to define this fashion. So what is actually happening here? I'm taking this operation on n. Of course, this operation would be unceasing, but it would be ever continuing. Well, it is on not it is better than to write this set right in the beginning. Okay, of course it is also not completely smooth. That here is smooth. We have proved that, right? We have proved that. And now the thing is, whenever we okay, that is n is of course smooth, n is defined very clearly. So let's leave n, but here let's do the parentheses, right? Oh, that is not quite clearly that it is that yet, but that is clear that we have just proved that it is the case, right? Here, of course, yeah, P of n is true was defined exactly like that, right? That is true. All right. And now we could just start to establish the shape of the set, right? Then we would go into it and we would look. Right. So first thing, well, how would we like to order elements in this set? Well, first thing would be then what? Oh, wait. Of course, I meant excluding 0, like we did it. Right. Uh, right. First thing would be what? Well, first thing we would like to look in. Oh, we know that the numbers are ordered, so first thing we would like to look at would be in this interval, right? All right. This is the first thing we would like to look at, and without 0, so exclude that, right? And that thing would be, of course, 1, as we have established that this can contain only 1. But okay, after that, we would have established the next interval, right? We have established the next interval, and the next interval is... okay, we have done it like that, right? Done it like that. But okay, 1 we already have. Okay, 2 we don't have. We haven't defined yet 2. But okay, we would like to have the next interval, and we just know that this interval here is exactly this interval. And by procedure in the upper proof, we know that it is this interval. right? This is this interval, and that this is this, right? And we know there are no real numbers in between, because, well, between 0 and 1 plus 1, we are just none, right? All right. And now we know that all natural numbers, all of them have that shape, right? Right. So writing down here 1 plus 1, it's completely okay. Right. And now we have really established the set of natural numbers, and we can go and establish the equality of this set to the set of these things here. Right. That would be very easy. We would just go and check that operationally one by one for each number, right? We would just check what this set is. So the big thing is we are now allowed to write this because we are now allowed to write an object that formalizes such thing in a mathematical language. That is, this object now exists in our mathematics. This object didn't exist because its real form, its actual form is this. It is in our system of axioms, right? In our system of axioms, the true shape of this object is this one. I mean, the true shape of this object is this one, not this one. This one is something funny, but by means of knowing that the natural numbers look like that, we can go further and further establishing their shape, right? And then we just say, well, just use induction. Use induction. And again, that would be very easy. Well, okay, actually, we have already established that, I think. No, well, we haven't established quite that, because we have only established that this set is inductive. But okay, now we would have that natural number is like that, right? And then you would have to establish that the natural number n. Okay, we would have that is exactly a sum of ones, and actually we had in the proof above that this is the sum of ones like this, that this is n plus 1, which is exactly plus 1 plus 1, right? Where this is that, right? We had that, right? And well, so we can establish that claim for all natural numbers that a natural number of this form is of this form. We actually had that in the above proof. We just didn't state it clearly, right? So yeah, it works perfectly fine. Right, let's write it properly. That is that, and then plus 1, right? And you see, we haven't even once stated, well, that is 3 times, that is 4 times, that is whatever times. We always only did one single step. And we used the iterational axiom that such objects or that such iterations over steps are even a thing, right? And that they can yield something, right? But we also saw there are sets for which it is perfectly fine. Well, so let such iterations be defined for sets for which it is perfectly fine. So it is fine. Okay. And now, indeed, each other natural number will be defined in terms of this iteration. So basically what we are writing down here is an iteration on an ever increasing set, meaning that this is, one excluding zero, ever increasing set. Now we go to this, because when this is defined, then we can go to this, right? Because that is the already defined set. We can go onto this, right? Here 1 plus 1 plus 1, because that is already defined, so we can go to this. And this iteration kind of never ceases, and the whole set is comprised by this, right? But how we would uncover this set? Well, we would uncover this set in that way. Mathematically, we would say, well, this is defined, then we go to this, and then we look at what is actually it. What is it actually? Well, that is that number, and the operation gives that, and that would just go on with those operations, go on like that. And you see, at no point we actually use number of times something. It was all phrased in different terms. It might seem weird and funny. Let's write a familiar shape of natural numbers follows from the proceeding in the theorem. Shape of n follows from the proceedings in the theorem. Right, but it was warranted because we wanted to base it on a more axiomatic object, and this more axiomatic object was iteration in the iterational axiom. And then this was perfectly defined because we only used one step thing, and we used the language of iterations, but since we introduced him as an axiom, it was perfectly defined. And that axiom was also warranted, as I told you, that there are some sets that actually well perfectly fit the notion of seeking iteration, right? And that way we derived the natural numbers, and now we define counting. We define that having something one time means that we have such an object, we have such a collection of objects which we can bijectively map to the set. Oh, that is the set and 0. We can map that number of objects, let's call it I or something, bijectively to the set. This is the number 1. Define counting via bijections on n. Via bijections. Actually on n on those actually no, on those, right? Because now we also know that they are ordered like that, and we know what it is that this knowing that actually that set is just cool. Okay. And actually no. Should be more careful from the proceeding in the above theorem. And well, need not necessarily understand it step by step, really justifying everything. You could do that, but I'm not doing it anymore because it's like obvious from the structure what is happening, right? But we are just establishing natural numbers, so you can just count with them as you like. And when you understand mathematics as essence of thinking more, you can return to that and then you can think about that. So this abstract stuff with iterations and things like that, and that I actually wanted to define it like that. You don't need to really understand that to deal with the course. It is just that I wanted to establish it properly, very properly. Okay, well, that is okay. Okay, whatever small or equal n, right? Okay, small or equal n. Okay, in natural numbers, of course, just like n. Okay, a set m contains n elements if there is a bijection f, and the main word is here bijection, right? One to one. And we define counting like that, and we really do define counting like that, nothing else, okay? And we know what this set looks like, and we know that this is some n. And as usual, we call that adding one n times, and you know that it is constantly adding one just from the structure of this set, right? But we call it adding one n times because one n times because, well, to our iterations of operation plus, we could apply this bijection thing, right? We could apply this bijection to the steps that we do here. And this bijection be applied to this because, well, this bijection would be exactly this, right? So we kind of defined natural numbers in a very abstract way, which is kind of nice somehow, I think. Yeah, that's nice. That's actually nice if you think about it, that you can have such an abstract approach that is entirely based on one step thinking, well, with some circumventing, but it is nice. It is nice to think about it in different ways. Right, okay, well, follows from the proceedings in the above theorem. So, and actually you could establish it really very, very properly. You could establish it very, very properly. So, somewhere that is good, right? And yeah, you could establish very, very properly that really counting works and things like that, that it has this shape, and you can really see how counting kind of arises from one iteration steps. And this is somehow magnificent in my opinion. This is very interesting. Like we have abstractly defined counting via some abstract reasoning and things like that. Funny, right? Okay, well, okay, we also define as usual, and that means just like always, right? Just use that, understand that as definition. 1 plus 1, that is just equal to, so 2 is defined as 1 plus 1, 3 is defined as 1 plus 1 plus 1, and so on. You know the names. Right, I thought that we will also define right away integers and rational numbers, and there is not a lot to do, but okay, for now it suffices. So we have defined the natural numbers. That's great. And next time we define integers and rationals, and we'll already proceed with some stuff because to define integers and rationals is now not a big case. It's done very easily. Okay. Okay.